In 1977, an astronomer saw a signal. It was so strange, so bizarre, he wrote one word on the date to print out. He wrote, "Wow," in the margin. That signal, that moment, it opens the door to something, to these radio signals from deep space. They're not a steady hum, they're sudden, they're brilliant shouts. And then they vanish, they disappear as fast as they come. We're going to look at 15 of these signals, the most baffling ones ever heard. And by doing that, we might find the biggest clues. Clues to how the universe really works. There are bursts that repeat. They come with clockwork precision. And there are signals that seem to come from nearby. From our nearest stellar neighbors, we have to ask what they are. Are they the death cries of stars, or are they something else? Are they a first greeting from another world? So the question is in the cosmic static. What do you believe is waiting? Jerry Amon was a volunteer astronomer. He was looking over the printout from the Big Ear telescope. It was a summer night. The machine printed the universe's radio noise as letters and numbers, mostly ones and zeros, just a quiet static. But on August 15, 1977, there was a sequence. It reads 6EQUJ5, a 72-second spike. It was 30 times louder than the empty space around it. Amon circled it in red pen. In the margin, he wrote one word. Wow, that's how it got its name. The signal came from the direction of Sagittarius, near a star group called Chi Sagittarii. Everything about it was strange. It was a narrowband signal, tuned to one specific radio frequency, like a radio station. That's a key marker. Natural cosmic events usually broadcast across many frequencies. This was just one. For 72 seconds it blared, then it was gone. It has never been heard again. Astronomer Jill Tarter called it the most famous candidate signal we have. Its perfection is the mystery. If it was natural, why has nothing like it been found since? Some said it might be emissions from a passing comet, but the timing and location didn't match. Others think it was a one-time astrophysical event, a cosmic flare we don't understand, but its characteristics keep another possibility alive, that narrow, powerful, fleeting shout. What if for 1 minute and 12 seconds we heard a beacon, a signal not meant for us, but one that passed through our solar system by chance? The wow signal is the ghost at the beginning of this story. A hint that in the vast quiet, something might occasionally choose to speak. That one word, wow, on a printout, it left a question hanging for decades. What if a signal like that came back? Then, in 2012, from the Arecibo dish in Puerto Rico, an answer started to form. It wasn't a long tone, it was a flash. A blip of radio energy, just a few thousandths of a second. Catalogued as fast radio burst 121,102. At first, it seemed like another cosmic oddity, but then it happened again. And again, this was the first repeater ever found, a signal from deep space that refused to stay silent, that changed everything. Before this, scientists thought these bursts might be final events. A catastrophic explosion from a dying star, something that could never happen twice from the same spot, but a repeater meant the source survived. It was something that could fire over and over for years. As the astrophysicist Shami Chatterjee said, the repeating bursts tell us the source is not destroyed. It can fire again and again, so that pointed away from a one-time collision. It pointed toward a persistent cosmic engine, something like a highly magnetized neutron star, a magnetar experiencing powerful starquakes, or maybe the turbulent environment around a young black hole. Tracing its origin was a feat. The signal came from a tiny, faint dwarf galaxy, 3 billion light-years away. To put that in perspective, the light we're detecting now left that galaxy when life on Earth was just single-celled organisms. The burst traveled through the thin gas between galaxies all that time, and that left a specific fingerprint called a dispersion measure. It let astronomers calculate how much material it had passed through. They could map the otherwise invisible cosmic web, and this repeater lives in a region of that distant galaxy that's busy forming new stars that suggests a link to young, energetic objects. Like those magnetars, but the precise mechanism what can launch such a brilliant millisecond flash across the universe that remains elusive. The fact it repeats so sporadically with no predictable pattern, it fuels a deeper wonder. Could this be a natural cosmic lighthouse, spinning and flashing by the laws of physics alone, or does its stubborn reappearance hint at something more intentional? A beacon designed to persist, to be noticed. This mystery from a galaxy 3 billion light-years away, it makes the next signal, one from astonishingly close to home, even more perplexing. 3 billion light-years, it's a distance that's almost impossible to really think about, but the story of these radio signals, it doesn't start that far away. It starts much closer, with a signal so strange that when it was first seen, they just erased it. This was 2001, at the Parkes Radio Telescope in Australia. An astronomer, Duncan Lorimer, was looking through old data. His student had found something, a single spike in the recordings, a blast of radio waves just 5 milliseconds long, but so powerful it overloaded the telescope. The first thought was that it had to be interference, something local, a satellite passing by, or maybe a microwave oven in the kitchen. They flagged it. And then they dismissed it. The data point was actually deleted from the main catalog, but Lorimer kept thinking about it. The signal's fingerprint showed it had passed through a huge amount of dispersed matter. More than anything inside our own galaxy could account for, which meant its origin wasn't just outside the Milky Way, it was billions of light-years beyond it. That 5-millisecond blip, what they now call the Lorimer burst, had crossed an unimaginable void, and in that instant, it released more energy than our sun puts out in 300,000 years. Astronomer Matthew Bales later said it was so bright and so far away, it forced everyone to rethink what could produce that kind of energy. This was the first fast radio burst ever documented. Though nobody knew that at the time, it opened up a whole new field, built on catching these cosmic lightning strikes. The key clue was in its dispersion. The different frequencies of the burst arrived at slightly different times, stretched out by the thin gas between galaxies. That high dispersion measure was like a logbook of its journey. But when astronomers pointed every other kind of telescope at that spot, optical, X-ray, gamma-ray, they saw nothing. No afterglow, no remnant, no source. It was a shout in the dark with no visible speaker. That singular nature is what fuels the deepest speculation. We know now that some bursts repeat, but this one never did. It was a one-time event. Maybe it was the final, catastrophic merger of two neutron stars, a collision so violent it warps space-time itself, or maybe it was the snapping of a cosmic string. A flaw in the fabric of the universe from its earliest moments. The energy scale invites bigger questions. Could a focused, tremendous release of power like that be engineered? Some have cautiously proposed that for a civilization far beyond ours, a burst like this could be a side effect of immense propulsion systems, like light sails powered by giant radio beams. It's a reminder, when nature performs a magic trick, you have to first rule out the possibility of a natural miracle before considering anything else. The Lorimer burst was a solitary event, a brief, brilliant anomaly that rewrote the textbooks, but its legacy is the search for a pattern. It makes you wonder. If a signal that powerful can be a random accident, what does it mean when a signal repeats with mathematical precision? Precision is what you're after. A repeating signal, something predictable, but then there's the kind that comes from where nothing should be. Back in 2004, something showed up. Not from one big telescope, but from millions of home computers. That was SETI at home, a screensaver letting people donate their computer's idle time to sort through cosmic radio noise. And in all that, a faint pattern got flagged. They named it Arecibo 02 plus 14A. It was very weak, but it was picked up 3 times, and it had 2 odd things about it. First, its frequency was near 1420 MHz. That's a quiet band between the natural emissions of hydrogen and hydroxyl. They call that the water hole, a logical place to listen where someone might broadcast to be found. Second, the signal drifted. Its frequency slid over time, smooth and steady. That drift is a clue. It matches what you'd see from a rotating planet. As it turns, the transmitter's motion would shift the frequency, like the pitch of a passing siren. And this drift rate, interestingly, lined up with what you'd expect from an Earth-like world. But when they looked at the coordinates, there was a problem. It pointed to a blank patch of sky near Pisces. No obvious stars, no planets, no galaxies. SETI researcher Dan Wertheimer put it cautiously. He called it interesting, but said without repetition, it's just a candidate. The big challenge is always interference. A cell phone glitch, a satellite, even a microwave oven in an observatory kitchen can mimic an alien signal. The most likely explanation for Arecibo 02 plus 14 is human-made radio interference, or maybe a rare pulsar glitch, but its profile makes you think. What if a distant civilization is using a narrow beacon, sweeping it across the galaxy like a lighthouse? Our solar system might pass through that beam only now and then, catching a whisper when the orbits align. That would explain why we hear it sometimes and why the source seems to point to empty space. The beacon could be far behind that point. This signal is the ultimate needle in a cosmic haystack. A whisper right at the edge of what we can detect. It raises a question. How do you separate a hopeful message from the stars from the electronic murmur of our own world? That line gets blurrier when the signals we find don't just whisper. They come with a rhythm so strange, so artificially perfect, it doesn't match anything we expect from nature. A rhythm is a different kind of clue. It suggests order. In 2018, the CHIME telescope in Canada picked up a signal with a rhythm. It felt almost mechanical. It was called Fast Radio Burst 180,916. This one repeated, but it wasn't random. It followed a schedule. For about 4 days, it would fire off bursts. Then it would go completely silent for around 12 days. Then it would start again. The whole cycle took 35 days, a cosmic clock ticking across 500 million light years. That precise timing was a gift. It pointed strongly to an orbital dance. Picture a highly magnetized neutron star, a magnetar, in a long, slow orbit, orbiting a companion star or maybe a black hole. For part of its orbit, its powerful bursts are aimed at us, like a lighthouse beam sweeping across a dark shore. Then it swings behind its companion, or into a position where the emissions are blocked and the signal for us goes quiet. Astrophysicist Ziggy Plunis noted that this periodicity gives a clue about the environment. It suggests a binary system where the bursts are modulated by orbital mechanics. That natural framework helps explain the rhythm, but the implications are deep. The signal itself has a lower dispersion measure than many other fast radio bursts. That means it traveled through less intergalactic material, which fits with its relatively closer origin in a spiral galaxy. It was traced to a region busy with star formation. The perfect nursery for young, violent objects like magnetars. Yet that 16-day cycle is so clean, so predictable, it makes you wonder, in a universe filled with chaotic explosions, what are the odds a natural process creates a pattern so neat, so regular that it stands out like a metronome against the random noise? Is it just the fortunate alignment of a cosmic orbit, letting us witness a natural phenomenon with perfect timing? Or does that very regularity serve a purpose? If you wanted a signal to be recognized as artificial, as something beyond natural chaos, you might encode it with a simple, repeating interval. A pattern that declares, "I am here." The 16-day cycle of FRB 180,916 sits right on that edge, between a natural celestial dance and a potential signature. It shows the universe can create its own intricate clocks, but it also makes you listen more carefully to the next signal, one that didn't just have a rhythm but seemed to carry a message. Written in prime numbers are a mathematical signature. They don't just show up in cosmic static, but if the signal came from next door. In 2020, the Breakthrough Listen project picked up something, a narrowband radio signal at 982 MHz. It seemed to come from Proxima Centauri, the star next door. Just over 4 light-years away, they called it BLC-1. This was different, not some distant flash from a billion years ago. This was from our immediate neighborhood. A place we know has a rocky world, Proxima b, right in the habitable zone. The signal drifted in frequency, like it would if the transmitter was on a moving planet. It wasn't a blip, it lasted for hours across multiple sessions. When the telescope moved off Proxima Centauri, the signal disappeared, so it was from the sky, not Earth. For a moment, the possibility was there. As Andrew Simeon said, it had interesting characteristics, a technosignature, a whisper of technology from the closest star. A place we might reach. The implications were huge. It would mean we're not alone, and our nearest neighbors are close enough for a conversation, messages taking just over 4 years each way. But hunting for alien signals is about elimination. The first suspect is always us. Our planet is drowning in radio noise, satellites, cell towers, aircraft, bad electronics. The team dug deeper. They looked for harmonics, for the echoes of human tech, and they found them. The signal's fingerprint matched harmonic interference. A byproduct of our own civilization, reflected off something just right to look like it came from space. BLC-1 became a lesson in caution. An extraordinary claim needs extraordinary evidence. And the evidence, under scrutiny, pointed home to Earth. That doesn't diminish it, it sharpens the search, it teaches a lesson. The most exciting signal is often the one you can explain. Because each false alarm helps build better filters, helps ask sharper questions. The story of BLC-1 is about hope tempered by doubt. It shows the challenge of listening from inside our own noisy bubble. If a signal from the star next door can be mimicked by our own tech, what does that say about whispers from thousands of light years away? It demands a deeper proof. A signal has to survive every test. It has to carry a mark that nature can't forge. That search for an unmistakable signature turns us back to the deep cosmos. To a signal so bizarre, its very location defies everything. 7 billion light years, that's the distance this signal traveled. FRB 190,523. It was detected in 2019 by the Deep Synoptic Array in California. A single, brilliant flash. It had been moving through space for over half the age of the universe before it reached us. An immense amount of energy released in a millisecond. And it came from a time when our own galaxy was still young. What was puzzling wasn't just the power, or that it was a one-off burst, it was where it came from. Up until then, the repeating bursts, the ones we'd traced, they came from small, turbulent dwarf galaxies, places full of young stars being born, violent places, which fit the idea that magnetars, these young, intensely magnetic stars, were the source. But FRB 190,523 didn't come from a place like that. It came from a massive galaxy. A mature one, a quiet place where the frenzy of star formation had settled down long ago. Vikram Ravi, a cosmologist, pointed this out. He said this burst shows fast radio bursts can happen in a variety of galactic environments. Not just in dwarfs, that observation changed things. It meant the source of these flashes couldn't only be linked to the drama of young stars. The possible causes had to include older stellar populations too. So even the quiet, older neighborhoods of the universe, they might still hold cataclysmic events. The signal itself confirmed the journey. Its dispersion measure was high. That's the stretching of its frequencies. It acted like an odometer, tallying all the thin, invisible gas it passed through over those 7 billion years. And when other telescopes looked for an afterglow, any flash of gamma rays or visible light in that spot, they found nothing, just silence after the burst. So what could create such a focused, immense release of energy in a calm galaxy? One possibility is a rare collision. A black hole merging with a dense neutron star. A final, violent event that rips the neutron star apart. Another, more exotic idea is a cosmic string snapping, a theoretical flaw in space-time from the universe's first moments vibrating as it shifts. But beyond the mystery of its source, this distant signal has another use. It's a tool. As the burst traveled, its waves interacted with every atom, every stray electron in the cosmic web between galaxies. By measuring how the signal was stretched and delayed, astronomers could weigh the invisible. They could map the distribution of the missing matter. The matter theorists say must be there, but we can't see. This signal from 7 billion light-years away became a probe. A single flash illuminating the dark scaffolding of the cosmos. It shows these mysterious events have a dual nature. They're profound puzzles and they're precise instruments. And if a signal from such a distant, ancient place can teach us about the structure of everything, then what could we learn from a pattern that seems to come from nowhere? A pattern that repeats with a cadence so strange it feels like a countdown. Looking for something that repeats, that gives you another chance to hear it, that's the whole point. But sometimes the most interesting thing only happens once. Back in 2015, a signal came in. It was from a star system about 95 light-years away, in the direction of HD 164,595. That's a star like our Sun, and we know it has at least one planet, a Neptune-sized world. The detection was made by the Ratan 600 telescope in Russia. It was a strong signal tuned very specifically to 11 gigahertz. That's a frequency we use here for military and satellite communications. The power of it was the striking part. If it was meant as a general broadcast, a shout to the whole galaxy, the energy needed would be immense. It would require something like the total output of its star. A civilization that could do that is hard to even picture, but there's another way to think about it. If the signal was a narrow beam aimed right at our solar system, then the power requirement becomes more reasonable. It would be like a spotlight, and for that moment we were in it. SETI astronomer Seth Shostak talked about it cautiously. He called it a candidate worth checking again. The main issue, he noted, is that it hasn't been seen since. That's usually what happens with interference, and interference was the most likely explanation. A secret military satellite, or some piece of our own technology passing through the telescope's view, could create a signal that looks exactly like it came from the stars. The star itself is interesting. HD 164,595 is a little older than our Sun, but very similar. A stable, long-lived star is the kind of place you might expect a civilization to have the time to develop. The planet we know about is a gas giant, not a place for life as we know it, but where there's one planet, there are often others. There could be rocky worlds we just can't see yet. So you're left with this compelling, frustrating maybe, a single, strong signal from a promising star, and it never came back. It's the perfect ghost. Was it some natural event from that system, a kind of radio flare we've never seen before? Or was it, for just a brief moment, a targeted message, a hello that we heard, but by the time we turned to listen more closely, the speaker had gone quiet? These one-time events shape the search. They're whispers that force you to build better ears, to have more patience, because to ever understand a signal, you need to hear it more than once. You need to see a pattern come out of the silence, a pattern that shows you not just a source but an intention. 12 million light-years away, that's practically next door in cosmic terms. And in 2020, astronomers did something. They pinpointed a repeating fast radio burst. They found it in a specific, ancient neighborhood, not in some distant, star-forming dwarf galaxy, but in a globular cluster orbiting the grand spiral galaxy M81. This signal, FRB 22120E, became the closest known fast radio burst to Earth. A cosmic laboratory suddenly within our reach. Its location was the first shock, because globular clusters are dense balls of ancient stars, some of the oldest structures in a galaxy. They're quiet retirement homes for stars, not the violent nurseries where young magnetars are born. Finding such a powerful, repeating signal here broke the rules. As astronomer Franz Kirsten noted, it forced everyone to consider new formation channels. It meant the recipe for a fast radio burst had more than one ingredient. And because it's so close, the signal itself is different. Its energy is lower than its cousins from billions of light-years away. It's a quieter shout. But because it repeats, we can study it in exquisite detail. Networks of telescopes, like the European Very Long Baseline Interferometry Network, can combine to watch it, listening for its next murmur with incredible precision. So what could be causing it in such an old, calm place? The suspects are fascinating. One leading idea involves not a young magnetar, but an old, dense stellar remnant. A white dwarf. In the tight gravitational dance of a binary system, two white dwarfs could merge, creating a brief, magnetized powerhouse capable of these eruptions. Or perhaps it's something even more exotic, like a quark star, a hypothetical, ultra-dense object where matter itself breaks down into its fundamental components. This nearby signal teaches a lesson. It shows the universe can create these brilliant flashes through multiple pathways. By studying FRB 22120E, we get a clearer, closer look at the engine. We can test our theories against a signal that hasn't been stretched and faded by an epic journey across the cosmos. Understanding this galactic neighbor helps us interpret the faint, distorted whispers coming from the far edge of everything. If such different environments can produce similar signals, then what we're hearing might not be one mystery, but many. And that realization makes the next signal, one that seems to defy the very laws of physics, even more startling. The universe's biggest mysteries can come undone by the smallest flaws. Back in 1997, at the University of Western Sydney, a research team thought they had a breakthrough. They found a persistent, narrowband radio signal. It was tuned to 1420 MHz, the hydrogen line, a quiet, significant channel in the cosmic radio dial. And it seemed to be coming from the Tau Bootis star system, a system we knew had a planet, a hot Jupiter, orbiting dangerously close to its star. For several nights the signal held steady. A constant, unbroken tone from one point in the sky. That stability was the key. Natural cosmic radio usually wavers, it drifts. This one didn't. For a moment the possibility shimmered. Could this be a beacon, a deliberate transmission from a star system with a known world? Astronomer Ragbir Bathel was part of the work. He remembers the initial excitement and then the meticulous process of elimination. He said they had to rule it out carefully, that it's a lesson in how pervasive human-made signals are. So the team began the forensic work. They checked and rechecked their equipment. They looked for patterns that might betray a terrestrial source, and they found it. The signal wasn't a whisper from the cosmos. It was a hum from a faulty electronic device right here on Earth. A piece of their own technology was mimicking the perfect, artificial-looking signal they were hoping to find. When they fixed the equipment, the signal from Tau Bootis vanished. It had never been there at all. The star itself added another layer of sobering context. Tau Bootis b, that hot Jupiter, orbits so close to its star that its dayside temperature could melt iron. It's a world of scorching, violent extremes, not an ideal place for life as we know it. This episode is a foundational cautionary tale. It underscores a profound challenge. Our planet is wrapped in a dense, invisible shell of our own radio emissions. Satellites, cell phones, radar, even a loose cable in an observatory can create a convincing cosmic ghost. So how do scientists improve? They build in redundancy. They use multiple telescopes, continents apart, to verify a signal is truly from the sky. They develop sophisticated software filters to recognize the digital fingerprints of human interference. They look for signals that show Doppler drift, that telltale frequency slide caused by a transmitter on a rotating planet. Every false alarm, like the one from Tau Bootis, makes the search smarter. It forces a more rigorous validation, a deeper skepticism that has to be satisfied before any claim can be made. This relentless weeding out of the mundane is what makes the remaining, unexplained signals so compelling. Because when you eliminate every possible source of interference, every known astrophysical event, what you're left with is the truly unknown, and sometimes that unknown doesn't just whisper. It arrives with the force of a cosmic sledgehammer, carrying energy from a source that seems to defy the very laws of physics. The line between natural and artificial can flicker. Pulsars are the universe's most reliable clocks, spinning neutron stars, sweeping beams of radio waves with metronomic precision. But then one of these cosmic clocks started to blink. That's Pulsar B 1931 plus 24. For years it was steady, then astronomers saw it vanish. Its radio pulses would just stop for weeks. Then they'd switch back on. This wasn't random. It followed a 35-day cycle, active for about a week, broadcasting its ticks, then completely silent for roughly a month. When it was on, it was a perfect, predictable clock. When it was off, it was as if the star was unplugged. That on-off pattern felt deliberate. It mimicked what an intelligent signal might do. A beacon conserving power or drawing attention through its pattern. It captured the interest of those searching for extraterrestrial intelligence. Could this be a sign? Andrew Lyne helped unravel it. He called it a cosmic lighthouse with a faulty bulb. The mechanism is natural but incredibly complex. It lies in the pulsar's magnetosphere. That intense, swirling cloud of charged particles trapped by the star's magnetic field. For the radio beams to form, this plasma has to flow in just the right way. In this pulsar, that flow periodically stalls. The conditions for the beam just shut down, like a river freezing over. The water is still there, but it can't flow. Then something shifts internally, the ice breaks, and the river runs again. This switching is likely tied to starquakes, or to shifts in the superfluid vortex C inside the neutron star's crust. These events can cause a glitch, a tiny sudden increase in the star's spin. That release of energy might trigger the magnetosphere to reconfigure, turning the radio beacon back on. So this intermittent pulsar sits at a crossroads. Its behavior was so orderly it sparked thoughts of design, yet deeper study revealed a profound natural process. Nature can create patterns of stunning regularity, patterns that look for all the world like a choice. That insight is a crucial guide. Look first for the exotic physics within known objects. Before leaping to other explanations, ask if a star, in its immense and violent complexity, could be putting on this show. Pulsar B 1931 plus 24 is a masterclass in cosmic impersonation. The universe is full of actors capable of performances that challenge our assumptions, and if a pulsar can mimic a beacon so perfectly, it makes the next signal even more compelling. One that didn't just turn on and off, but seemed to carry a message, written in the most fundamental code of mathematics. A star that flickers like a broken street lamp. It demands attention. Kick 8,462,852, Tabby star. Its light doesn't just dip in a regular rhythm, it plunges erratically by huge amounts for days at a time. The main natural explanation is a vast swarm of comets, but even that stretches our understanding. Then, in 2016, the Green Bank telescope recorded a narrowband radio signal. 6 GHz from that same patch of sky, and speculation ignited. Could this be a technosignature, a civilization building something colossal around its sun? A structure harvesting stellar energy, causing those dimmings. For a moment, the pieces fit, a weird star and a curious signal together, but science requires more than a moment. A single detection is a starting point, not a conclusion. The signal was never seen again, not by Green Bank, not by the Allen telescope array that listened afterward. The most probable culprit was a passing satellite, its radio chatter briefly aligning with the star's coordinates. The absence of a repeat signal spoke volumes. It suggested the radio whisper and the star's optical strangeness were a cosmic coincidence, not a conversation. Tabby's star itself remains a mystery. Its light curves are a puzzle. Natural astrophysics is still working to solve it, with ideas from interstellar dust to the remnants of a shattered planet. Yet the lack of a confirmed, persistent radio signal is a crucial data point. It tells us that even the most compelling circumstantial evidence, a star acting impossibly, needs the gold standard. A repeatable, verifiable signal to suggest intelligence. We are left balancing two forces, the open-minded wonder that asks what if, and the disciplined rigor that responds prove it. This balance is the engine of the search. It prevents us from seeing patterns in every shadow, while ensuring we never dismiss the one shadow cast by something new. And sometimes the most definitive proof we find confirms not a message, but a magnificent natural violence, a signal born from the death of a star, carrying the signature of a fundamental force of creation. The link was made inside our own galaxy. In April of 2020, a magnetar called SGR 1935+2154 erupted. This is a dense stellar corpse about 30,000 light-years away. It did something extraordinary. It erupted not just with X-rays, which these stars are known for, but with a simultaneous burst of radio waves. Lasting just a millisecond, telescopes on Earth caught it, the Canadian CHIME array, and a network of small antennas called STARE-2, which was built to catch nearby flashes. This was the first time a fast radio burst was traced to a specific, known object, and that object was a magnetar. The radio energy released was immense. But it was about 1,000 times weaker than the bursts we see from other galaxies. That difference in scale was the clue. Astrophysicist Chris Bochenek led the STARE-2 detection. He called it a smoking gun. We've seen a magnetar do what we suspected. This was the breakthrough, a direct observation that at least one source of these signals is the violent activity of a magnetar. So what happened? Picture a star with a magnetic field trillions of times stronger than Earth's. This field is like a cage of force wrapped around the star's crust. The crust is under strain. It can crack, a starquake. When it does, the magnetic field lines snap and reconnect. It's a process like a solar flare, but scaled to a monstrous degree. This convulsion blasts out high-energy X-rays and gamma rays. And as this magnetar showed, it can also launch a focused jet of radio waves. The association was clear. The X-ray burst and the radio burst were two sides of the same event. This discovery peeled back a layer. It provided a concrete model. A magnetar flare in our galactic backyard can produce a fast radio burst. So the immediate question follows. Could all fast radio bursts be scaled-up versions of this? Are distant magnetars in young galaxies having even more violent outbursts? It's a compelling answer for many of the signals. But the universe loves variety. We have bursts from quiet, old globular clusters, and we have the precise 16-day cycle of another repeater. A single magnetar model might not explain every signal's behavior. This discovery doesn't close the book. It opens a new chapter. It gives astronomers a template. A nearby laboratory to study the detailed physics of how a collapsing magnetic field can forge a whisper that crosses the cosmos. It guides the search, telling us to look closely where magnetars are born. But it also reminds us that a smoking gun for one mystery often reveals the outline of another. If magnetars are one source, what other cosmic engines are waiting to be discovered? The answer may lie in the echoes of the most ancient signals we can detect. For almost 20 years, the Parkes Observatory in Australia was picking up these strange signals. They named them Perytons, and they looked exactly like fast radio bursts from deep space. A sharp spike of radio energy, just a millisecond long, and they had that key signature, the dispersion measure. It seemed like they'd traveled through huge stretches of interstellar gas. They were perfect imposters, and they were a complete mystery that lasted from 1998 all the way to 2015. What was creating these precise, powerful bursts right there in the data? The clue was in a pattern nobody noticed at first. Researcher Emily Petrov led the work. She remembers the moment it clicked. It was a eureka moment, realizing the timing lined up with lunch breaks. The signals only happened during the day. And they clustered right around local noon. The telescope itself gave it away. Parkes has a huge, stationary dish, but it listens to a patch of sky that moves as the Earth turns. A real cosmic signal would drift slowly across the field of view as the source sets. The Perytons didn't drift, they were fixed relative to the observatory. That meant the source was on the ground, so the team put radio monitors around the facility, and they caught it. It was the observatory's microwave oven. If someone heated their lunch and opened the door before the timer went off, the magnetron, the part that makes the microwaves, would spark. That little electrical arc created a broadband radio pulse. That pulse would bounce off the metal walls of the building and go right up into the giant dish, which would record it as a celestial event. The pulse's specific frequency, around 2.4 gigahertz, matched the oven. It was a funny and humbling find. This grand search for cosmic mysteries was getting interrupted by someone's impatient hunger, but this was more than just a quirky story. It forced a major change in how radio astronomers filter their data. They built new algorithms to spot and throw out signals with a fixed terrestrial signature. They set up stricter protocols to shield observatories from local radio interference. The lesson of the Perytons is now part of the method. It teaches a deep humility. Before you can hear the universe, you have to learn to silence your own world. Every strange signal has to first run through a gauntlet of earthly explanations. Is it a satellite, an airplane, bad electronics, or a microwave oven? That rigorous vetting is what gives the remaining unexplained signals their weight. It means when a fast radio burst, like the one from the Magnetar, gets confirmed, the confidence is high. The Perytons show that the line between a cosmic discovery and a human lunch break can be incredibly thin. They show that the tools to find truth aren't just telescopes, they're skepticism and clever detective work, and being willing to laugh at your own assumptions. That whole process of elimination sharpens the search. It refines the instruments and the questions for the signals that really do defy explanation. The last signal came from a star that might have a world like ours. Back in 2011, the Allen Telescope Array was listening to stars with known planets. It had dozens of small dishes aimed at one star in particular, a star with a confirmed planet in its habitable zone, where temperatures could allow for liquid water, and from that direction a signal came in. It was narrowband, a whisper on one specific radio frequency. For a moment, it looked like a potential technosignature, the kind of signal an advanced civilization might produce. That sparked immediate analysis at the SETI Institute. But modern signal hunting is about instant cross-referencing. Researchers like John Richards there explain the process. He said every candidate teaches you something. Here it was about satellite tracking data. The team checked their logs against the known paths of thousands of human-made objects in orbit, and they found a match. The timing and the direction lined up perfectly with a passing satellite. Its routine transmission had reflected off something or slipped through the filters and mimicked a signal from the stars. This wasn't a failure, it was a lesson in the new reality of listening from Earth. Our planet is wrapped in a dense shell of our own electronic noise. From cell towers and aircraft to the growing number of satellites, the sky is noisier than ever. The ATA-1 signal showed a critical advancement, using multiple telescopes to triangulate a signal's true origin. And the importance of real-time data analysis to rule out interference in minutes, not years. That process keeps getting refined. Imagine a future search where every curious signal is instantly checked against a global, live updating database. A database of every satellite, every aircraft, every source of human-made radio noise. That system would streamline the hunt, letting researchers focus computing power and telescope time only on the signals that survive that vetting. It points to the need for unprecedented international cooperation, sharing tracking data across borders and agencies, and it demands better artificial intelligence to sift through the torrent of cosmic data in real time. To spot the one anomaly that doesn't fit any known pattern, this 15th signal, explained in the end, brings the journey to a quiet point. We've gone from a single word on a printout to a coordinated global effort that has to filter out the noise of our own civilization. These 15 detections aren't a collection of answers. They're a map of questions. Each one, whether it was a natural magnetar's cry or an unexplained repeating rhythm, has pushed the boundaries of astrophysics and expanded the methods of the search. They remind us the universe is capable of phenomena we're only starting to grasp, and they frame the enduring question. When we finally hear a signal that passes every test, that carries the unmistakable signature of intelligence from beyond our world, will we be ready to understand it? The search keeps going, listening patiently to the static, waiting for the next whisper that changes everything. We're moving into the era of the square kilometer array. The sky, it's not one telescope, it's thousands of dishes and antennas spread across 2 continents, South Africa and Australia. Together they form a single radio ear. A collecting area of about 1 square kilometer. The sensitivity is hard to grasp. It could detect a signal from a distant planet, a signal no stronger than an airport radar. It will hear whispers our current telescopes miss, but it's not just about hearing them. The design, spread out like that, lets it pinpoint where a signal comes from. With extreme precision, almost like triangulation but on a galactic scale, so we wouldn't just know the general direction, we'd know which star, which system. This changes everything. We could map fast radio bursts not just to a galaxy, but to a neighborhood inside that galaxy, telling us if they come from star-forming regions or globular clusters or the quiet outskirts. To handle the data from an instrument like this, you need a new kind of listener. That's where advanced AI comes in. Algorithms that sift through petabytes, millions of gigabytes in real time. Their job isn't just to find signals, it's to classify them instantly. They'll learn the fingerprints of human interference, satellite downlinks, rogue microwave ovens. Filter them out before an astronomer even sees the data. They'll recognize natural events too, pulsar glitches, magnetar flares, and they'll flag the anomalies. The signals that don't fit any pattern. That constant, intelligent sifting, it dramatically increases the odds of catching something truly novel. Avi Loeb has talked about this potential. That we might be on the cusp of discoveries beyond natural wonders. He says you need open minds paired with these sharp new tools, that the transformative potential lies in systematically searching for evidence we've only dreamed of. This future is built on international collaboration. Projects are moving toward monitoring the entire sky continuously. A live, all-sky radio movie, not isolated snapshots. Initiatives like Breakthrough Listen are expanding beyond traditional frequency bands, listening higher and lower, watching thousands of star systems at once. The goal is to leave no stone unturned, no frequency silent. In that data stream, we might find one of two things. The first is a signal of undeniable complexity. Not a steady tone or a simple burst, but one with intricate modulation, a layered structure that natural processes can't forge, a repeating pattern that encodes a universal constant. Pi or the prime numbers in a way that screams of design. The second possibility is equally thrilling, uncovering a completely new class of astrophysical object. Solely through its unique radio signature, something whose existence we never predicted. How would that reshape us? Finding a complex signal would answer the ancient question. Are we alone? It would expand the concept of life and intelligence instantly, change our philosophy, our science, our sense of place. Discovering a new natural object would reveal a fresh chapter in astrophysics. Show us a new way for matter and energy to interact on a cosmic scale. Both paths tie together every mystery we've explored, from the solitary wow to the rhythmic repeaters. Each signal has been a stepping stone, teaching us how to listen, how to doubt, how to hope. The next great signal is out there, drifting through the dark. And now, for the first time, we are building an ear capable of hearing its true voice. The universe isn't silent. It has this static, these strange conversations. There's the wow signal, that one strong burst, and then there are the repeating bursts coming from galaxies so far away. These whispers, these 15 signals, they show a cosmos that's alive. With questions, each one, whether we've figured it out as a starquake on a magnetar, or whether it's still a complete mystery, each one chips away at what we think we know. They make us build better tools, they make us be more patient, they make us hold our conclusions lightly. Going through these signals, you see something true about exploration. The biggest discoveries, they often start with a noise, a persistent, puzzling noise in the data. These cosmic events, they show this balance. On one side, you have the rigor of science. The discipline, ruling out microwave ovens, ruling out satellite interference before you ever claim a discovery. And on the other side, you have imagination. The reach of it, daring to think that maybe some pattern could be a message. That tension, it isn't a weakness, it's what drives progress. It's why we build instruments like the Square Kilometer Array. It's why we write algorithms to sift through tomorrow's sky, looking for a signature we can't even picture yet. Carl Sagan said it, the universe is a pretty big place. If it's just us, that seems like an awful waste of space. That sense of wonder, that feeling we're part of something vast, it fuels all of this, the search itself. With its false alarms and its moments where you catch your breath, it teaches us about the violent beauty of stellar corpses, about the invisible structure of the cosmic web, and about the profound challenge of listening from our own tiny, noisy world. So look at the evidence from these 15 signals. The natural explanations are powerful. They're elegant, they account for more of the mystery every year, but the possibility, even if it's faint, the possibility of a signal that didn't come from chaos, but from consciousness. That remains. What do you think is the most plausible source for these cosmic whispers that keep coming? And if a signal ever did arrive, one that passed every test, a whisper that was clearly a hello from across the stars, how would that change our world? How would that confirmation change everything? If you enjoyed listening for meaning in the static, subscribe for more. More explorations into space's biggest puzzles. Thanks for joining the search.